Hey guys, welcome to our another session and thanks for joining us. In this session I want to solve another problem. Then as always, let me introduce heat transfer from 10th edition from Mr. J.P. Holman. And let's go to the problem and solve it. This problem is from chapter 3, number 46, okay? Then it has two sections, and in this section we want to discuss about section 1, which is a relationship between problem number 46 and problem number 39, as this problem mentioned it. Okay, so let's get started and discuss about it. As you can see, an aluminum rod 2.5 centimeters in diameter and 15 centimeters long protrudes from a wall maintained at 3000 degrees Celsius. Okay, let me highlight these parameters and numbers. 50 centimeters long and 2.5 centimeters. The environment temperature is 38 degrees Celsius. The heat transfer coefficient H is 17 watt per meter square degree Celsius. So using a numerical technique in accordance with the result of problem 339, and obtain values for the temperature along the rod. Okay, so subsequently obtain the heat flow from the wall at x equals 0, and the hint is that the boundary condition at the end of the rod may be expressed by this formula. Okay, just let me highlight it. Where M denotes the node at the tip of the fin, the heat flow at the base is some equation like this one, and Tm is the base temperature, and Tm plus 1 is the temperature of the first increment. Okay, let's get to the whiteboard, but before I'm gonna go to the whiteboard, let me go to the problem number 39. Okay, this was the problem that I discussed about it and we solved it. Okay, and you can refer to the video and see what happened there. Okay, it was the equation for the points at the middle of the fin, but the point at the end of the fin has actually another relationship and equation. We should earn it and prove it. Okay, in the problem number 46, this is the equation for the tip of the fin, but the relay equation in problem 39 was for all the points at the middle of the fin. Okay, then with this explanation, let's go to the whiteboard and discuss and solve this problem. Okay, but as always, at the first of my presentation, let me just draw another picture. Okay, it has 4 points: 1, 2, 3, and 4, and all these stances are similar and equals delta x. Okay, then each element has a limitation for itself. Okay, imagine all of these are equals. Okay, so let me format okay? This distance is delta x over 2, as we can see, and this is delta x, this is delta x, and this is delta x2, okay? Then I can say that all the temperature at these elements are the same, and we know it as T4, okay, as T4. All the temperature in this element are the same. These points, every place of this element, okay, this rectangle are the same, and we know it as T3 because this point is 3, named 3. And all the temperature everywhere of this element will be T2, and finally in here all the temperature will be T1, okay? So I should mention that equation for finite difference form from these points number 2 and 3 are the same, and we calculated and derived it in problem number 39, okay? But this is different, and this is different. But in this problem number 46, I mean, we have temperature of this point, which is 300 degrees Celsius, okay? 300 degrees Celsius. And we don't know the equation to find temperature of here. So we need two sets of equation, one for the points at the middle of this fin, and an equation for the tip of the fin, which is number 4, the point number 4. Okay, let me write previous equation from problem number 39. As you remember that, it was, let me go to the book because you can see it better. Number 39. Yeah, this equation. Okay, I want to change this equation. As you can see it, I won't change it. Just I want to change the form of it, but it's the same. Yes, I want to write it in this way: Tm equals Hp over Ka delta x square T infinity minus parenthesis of T at the point n minus 1 plus T plus 1 at the point n plus 1, okay? And at the denominator we have Hp over Ka. It is multiplied by delta x squared and plus 2, okay? So this is equation for points here, point 2 and point 3, okay? We can find temperature of points 2 and 3 from this equation. But how about number 4? We want to derive it here, and the final result will be this equation from problem number 46. Okay, this equation, okay? we want to derive this equation, then in this section and this section 1, I want to derive this equation. Okay, then let's get started. Okay, I want to separate just element 4. Okay, element 4. Okay, here is some fluid. This is number 4, point number 4, and this is number 3. Okay, we have fluid here, and T infinity is located someplace in here. Okay, so we should write equilibrium equation for that. Then let me write it. Energy in left phase equals energy by convection. Energy by convection, because all the convection system will be actually treated in up, down, and the right phase. Okay, then I want to write an equation for this equilibrium situation. Then what should I write? I have to write here. From the left, we have just conductivity minus Ka dt over dx over 2, because this distance is delta x over 2, as we discussed it before, and I will show the x or delta x not different. Okay, then it equal to HA T minus T infinity. Okay, or better say Tm, T or Tm. Okay, not different. Okay, the heat coefficient and the system transfer from the right phase plus transfer of heat from actually a perimeter up and down of these fin. Okay, then I want to write HP, and P is as perimeter multiplied by delta X over 2. Okay, over 2 T minus T Tm minus T infinity. Okay, so I can write it in this way. Minus 2 Ka dt over dx equals h T minus T infinity multiplied by P delta X over 2 plus A. Okay, then it will change to dt over dx equals h over 2 Ka T minus T infinity. It would be multiplied by P delta X divided by 2 plus A. Okay, sorry, I made a mistake someplace of that. Oh, let me think. Oh, great, correct. Then we can write it like let me write it here. dt over dx equals h p delta x over 4 Ka. Okay, if I multiply these terms to these two terms, okay, it would be something like that, plus h over 2k, okay, multiplied by tm minus t infinity, and this is tm, yeah, and this is tm. Okay, this is our relationship. Okay, let me name this equation number 1, but I need another equation, infinite difference. I want to just tell it, just we have a relationship when we have a geometry like exactly like this one. The right side is kind of fluid and the left side is kind of material or solid. So at the left we have conductivity, and at the right we have convection. Okay, so in this situation we can write this finite difference form or equation. Okay, just in this situation, dt over dx equals t at the point m minus 1 or t number 3, I mean number 3, okay, minus tm, which is t4, divided by 2 multiplied by delta x. Okay, I don't wanna discuss and prove it, but in another video maybe I will be focused on that and talk about it and say why we have this equation. And I want to name this equation number 2. Okay, then I want to write these two equations with each other. Just let me raise, because I need some place for keep continuing and keep going. Okay, let me change the color, and this was number 1 and this is number 2. Okay, then 1 and 2, we have t at the point m minus 1 minus t at the point m divided by 2 delta x equals the right side of equation number 1, which is h p delta x 4k, sorry, this is 4k a plus h over 2k multiplied by t minus t infinity, temperature at the infinity. Okay, then I can write t m minus 1 tm equals hp delta x squared 2k a plus h delta x over k multiplied by tm minus t infinity. Okay, t infinity, and then we can write t m minus 1 minus tm equals hp tm delta x squared divided by 2k a plus h t m delta x divided by k minus t infinity, okay, multiplied by these two terms again. These two terms I should write it again. Delta x squared. This is p as perimeter. Sorry. 2ka plus h delta x over k. Okay. Then okay, I can write, let me yeah, then I can let me just don't have any choices to except to raise these two equations because I need some more places. Okay, then I can write Tm multiplied by h delta x k plus hp delta x square over 2k multiplied by area plus 1 minus t infinity multiplied by these two terms again, h delta x over conductivity coefficient, thermal conductivity coefficient, hp delta x square and 2ka, this is a, okay, minus t temperature at the point m minus 1 equals 0. Okay, then this is the same, exactly the same formula that you can see at this problem. Okay, here this is exactly this problem, this equation. Then I can change it in another form to find Tm, because I need to find Tm at the end of the point, at the tip of the tip of the fin. Then let me write this equation like that: T infinity multiplied by h delta x over conductivity plus h p delta x squared, 2ka, a as area, let me just write it again. Okay, it will be plus t at the point m minus 1. Okay, all of these will be divided by h delta x over k plus hp delta x squared 2ka plus 1. Okay, then this is main formula for us to find temperature at this point. Okay, so it was actually the result of this session. Let me just say what we did in this session. This formula is we'll use to find temperature at these points 2 and 3, as we said it before. Okay, but for number 4, for the point number 4, I should use another equation that we derived it just in this session. Okay, in this problem, which is this equation. Okay, just for point number 4. Okay, then I want to keep going to find temperature for all of these points in the next session. So I hope you enjoyed from solving section 1, of course, of these problems, and these two problems are related to each other, number 39 and number 46. Okay, so I hope you enjoyed it. Take care. Bye bye.